volume does not contribute significantly. On the top of it, we went to neutron experiments. And going to neutron experiments, you can measure the sublattice magnetization. And also you can measure the critical exponent in the sublattice magnetization. The critical exponent of the magnetization, beta, is the critical exponent. Well, was not the right one, and it was different. You see, this is the sublattice magnetization. In one case, this is the sublattice magnetization in the other. So it's very different. So volume effects have to be excluded. Piezomagnetism. If you apply some pressure in a given direction, you may distort the local octahedra around, or the local environment around each magnetic moment. And by magnetocrystalline anisotropy, you can produce some effects. But in the case of the manganese fluoride, this is possible. We cannot exclude it. Why? Because the relation between applied pressure and magnetization is a tensor. And symmetry in the lattice, the manganese fluoride lattice, allows the existence of that tensor. But in the other cases, the symmetry says, no, this tensor must be zero by symmetry constraints. So we can exclude piezomagnetism with this simple argument. So maybe in the manganese fluoride it's a good argument, but since manganese fluoride collapses with all the other data, we have to find an explanation for everything together. So piezomagnetism is excluded. We want to apply magnetic field, but big magnetic fields. And we found this funny result. We start the hysteresis cycle, and then there is a jump here, then go to saturation, then this is very low, okay, but we went up. And then before the spin flop transition, for those who are not familiar, I think probably everybody, but a spin flop transition is a transition where you apply the magnetic field parallel to the antiferromagnetic direction of alignment, and then the energy, magnetic energy, minimizes, flipping the moments perpendicular to the magnetic field. Okay? This is spin flop transition. Something that is observed in low anisotropy antiferromagnets. It's a magnetic field-induced phase transition. So coming down in magnetic field, at zero magnetic field, and going down, we still saw magnetization coming down without being reduced. And then suddenly start some cascade effects, avalanche effects. But it's interesting that when we were moving the field up, these effects were not observed here. Were observed after, well after that. So there was one behavior, two behaviors, and in a fairly strange way. More interesting, we could not let the crystal to forget this memory effect. There was only one way to do it. One way to do it. Move the magnetic field high enough to pass the spin flop phase. And yes, the moments going above the spin flop phase change completely the magnetic structure. And then when moving the field down, they had forgotten everything. So when they forgot everything, the behavior became much more, you see, much more symmetric in is like a starting all the time starting. The loop becomes symmetric. For different temperatures, we had different cascade avalanche effects. So that tells us that the problem is how the magnetization progresses, how this spontaneous magnetization or impurity-induced magnetization was progressing as we apply a big magnetic field. So that told us that the phenomena could be related to the presence of antiferromagnetic domains. Okay. So going through this, I can go on and on with this problem because there was a lot of papers published on this. This hypothesis of the antiferromagnetic domain will accumulate excess magnetization could explain the appearing of spontaneous magnetization, the saturation of the magnetization alloy fields, the universality law, and qualitatively the difference with volume magnetization, the memory effects in the magnetization versus age, and jumps in the magnetization isotopes. Because there were places where the walls were more comfortable than in others in the crystallographic scenario, because some included impurities and some did not. So some configurations were favored, and then was less energy required to move from one step to the other one. Okay, so the wall jumped rapidly because from one configuration to the next one that was spinning the wall configuration. Wow, so this is the summary of what has been observed, what I have been explained to you. The message is not so much the scientific problem that if interests you, I can give you references and you can go through it, but the message of how even in a small disturbance affect the magnetic properties of compounds. So it's related to what I was explaining you about disorder. Let us rapidly move into